Okay, good afternoon, everyone. Once again, thank you very much to NIJ and everyone, all the organizers, for inviting me. It's been a very good week so far, and I'm sure the end of the day will be good. And for those staying at the SWIGMAT meeting tomorrow, I'm sure it will be fun. Jose answered the question, forensic science in the 21st century, will trace evidence ever reach the next level? So you pretty much stole my thunder, because I was thinking, yes, we know that. We just watch telly and we know that we can do a lot of things. Of course, the resources are infinite, etc. Everything can be analyzed quickly. There is no uncertainty, which is a big thing, and the offender is always in the database. Now, in this talk, what I want to do, I want to do two things. One, probably expand a bit on a few thoughts and philosophical ideas that I've already mentioned on Tuesday. And the other part would be more to show you a little showcase of different projects we've been doing, mainly in collaboration with the Australian Federal Police, and try to answer this question. Sorry if I repeat this slide, but I think it's a very important one, especially when we have to deal with administrators, politicians, funding organizations, and so on. Our problem in trace evidence, does it work? Our problem in forensic evidence is really, in trace evidence, is really that the work is really labor intensive. It doesn't seem to work, so it's very labor intensive, and we don't always give very good value for the money, so to speak. So it's a real issue, and I asked the question the other day whether that could lead to phase out some types of trace evidence, which in a way would be terrible. So what can we do about that? I fully appreciate that actually this is very simplistic, but it's a good way to probably summarize the problem. We can try to reduce the time and hence the cost, or we can try to provide more value, more information out of the evidence. And if we can do both, really we are pushing trace evidence towards that diagonal line here, which would be absolutely perfect. So one way to improve the value of forensic trace evidence is really to make significant progress to address this could have come from syndrome. I'll repeat it. We have several talks, several people mentioned that. I think Louise McKenna did a wonderful job in her presentation. But we really need to bring more informative and more accurate conclusions. This is really needed. Glass probably pioneered this field for trace evidence, but it's only the starting point. Really, we should try to push that. And let's be serious about that. We shouldn't really put our hand in the sand. We can do a lot of research projects. We can do a lot of things by teaming up with local universities, teaming up with different organizations. For example, the European Fibers Group designed several times target fiber studies, things that maybe you cannot do with one single laboratory, but by teaming up, you can get a massive amount of data that can help to interpret cases. So there is a significant effort we have to do here. Now, I'll put myself in a very difficult situation here. Those of you would have probably recognized that this is a basic formula for the Bayesian approach. I don't want to go into the details here, but a general criticism is which values can we use here? And if we don't have accurate data, then the whole thing is totally useless. So we can't use it. In my opinion, this is pretty much throwing the baby out with the bathwater. Because first, we don't necessarily need fully accurate data. We can have very conservative estimates. I think Patrick Buzzini this morning showed very well that we can get data that is useful. And even Ken's little exercise at lunchtime show that we don't necessarily need to go to the extreme, but very quickly we can get very interesting data. And going even further, talking about fiber here as an example, this gives really a very coherent approach. And we forget about the maths. I'm totally mathematically challenged. the reality here is the process. The process is very good because when you look at it, we look at all these different factors that we normally deal in trace evidence interpretation. And it's put in a very coherent manner. So it helps to identify the relevant questions. Now, let's move a bit further. Another way, up to this point in my presentation, I talked about traditional forensic science, where we deal with, QK comparison and so on. I think we do a very good job here, especially for, do the job very well in the laboratories, etc. But there is an area which is pretty much new and Ken made a very good presentation on this point. We need to be proactive because forensic science is really changing. And if we really want to make it in the 21st century, we need to use forensic science in a very proactive manner, right at the start of the investigation, and to some extent, lead the investigation when possible. Try to be predictive, intelligence-based, and close to real time. This is especially important when we deal with major incidents, such as terrorism, bombing, and so on. Now, I think when forensic intelligence will really become more and more daily routine, I think trace evidence will have an extra value. And then more and more people will realize what we can do with trace evidence. One thing with forensic intelligence, the thing I think Ken made the point, which is very interesting, is we don't necessarily focus on the identification per se, but we try to make links. So everything is pretty much optimized. The whole system is optimized to make links between cases. And maybe we can look at a very general level of discrimination as long as we can make links. And down the track, this link might really crystallize and then become really evidence. So there are really very good people in this area who are doing fantastic work here. It's Olivier Ribot and Pierre Margot at the University of Lausanne. And I really advise you to read these papers and all the work from Olivier, because although he did a lot of work on burglaries, and maybe we might think it's not really important, the concept is really, really good. Now, the dilemma here, do we want 99.9% or even more nines if we want accuracy, which takes 6 months? Or can we say 80% is good enough if we are close to real time? So again, there's a trade-off. It's probably not compatible with the high demand of the justice system, but in an intelligence framework, it's probably good enough. The problems here are now more on the technology side, because traditionally we bring all the samples to the laboratory. So the laboratories use very heavy instruments. They tend to be large, etc., expensive, and it takes a lot of space. It takes a lot of time to do the analysis. And I mentioned the other day backlogs and so on. And quite often, in the worst case scenario, we are only able to provide a result when the investigation is almost finished. So you can understand it doesn't fit with what I said before. So what can we do here? So luckily, we've got technology which can help us. Now, I'll make the point here, technology is not science. And we really have to be careful and avoid gadgetries. So we don't want gadget, but we want technology which is fit for purpose. And to do that, we really need to remember the very strong criminalistics focus and the very strong criminalistics principles. We shouldn't forget that, otherwise we might fall in the technology trap. Oops, what happened? This is an example in a DNA lab. They have nowadays robotics. It speeds up everything. Maybe on the chemistry side, the closest we would have is probably when people do blood alcohol with GCMS, with automated samples, samplers, and so on. But we agree, it doesn't really work for traditional trace evidence. We cannot put a garment and a fiber on some kind of automatic machine that would do everything. So what I'm trying to do for this second part is to show you some examples of how we could help with this problem. All these little, well, not little, all these research projects basically have been done in collaboration with the federal police. I picked up these three because it shows different angles. One, it's hyperspectral chemical imaging. The idea here is to show that by using a new technology that combines two sets of information, which is in essence morphology and spectroscopic informations, we can bring interesting data. The other one is isotope ratio MS, which shows that really by going to the extreme of the discrimination, in some cases, that would bring really interesting information, despite everything I said before about intelligence. And the third one is lab on a chip, which is really a way to bring the lab to the scene or closer to the scene, as opposed to bring the scene or the scene samples to the lab. So hyperspectral chemical imaging, I think it's been around for a while. It's been a bit of a combination of factors why we've been involved in that. One is because we met with Dave Exline at the time when he was at ChemImage. Another one is because my colleague, Brian Reedy at UTS, bought an FTIR machine using the same sort of principle, and all the pieces fit together. Basically, the principle is the following. Light intensity in a system like that is recorded as a function of both wavelength and location. So for example, in general, you have some kind of matrix of pixels, and you can focus on one pixel and record the intensity at one wavelength, and then keep the same pixel, record the intensity at another wavelength, and so on. And then if you have the intensity versus the wavelength, it's typically a spectrum. Now we can do the other way. We can fix a wavelength and record the intensity of the whole matrix. And then we have a mapping, we have an image. So in one go, it's possible to have some spectroscopic information and imaging information. It can be used in different spectral ranges. As I said, we've been heavily focused in the visible range and FTIR, mid-infrared. These are the advantages for typical trace evidence work. It's non-destructive, it's normally fast. The techniques are well established, peer-reviewed, even if they are combined together. It does the job of several instruments, minimum sample prep, and side-by-side comparison and presentations of results. In some cases, you can even record little movies that can be shown to the jury, and so on. Some applications, I won't show all of them here, but Gemma Payne, who is here, is completing her PhD in this area, looking at ballpoint pen inks, roller ball pen inks, firearm propellants. She's been doing fiber, even bruise aging, latent fingerprint enhancement. And Mark Tatu and Catherine Flynn, Mark is here, have been using the mid-infrared system for fingerprints and for typical trace evidence in the case of Catherine. So for the instrumentations, you've got the details here. We're using a chemical imaging macroscope and a chemical imaging microscope for the visible range. And for the mid-infrared, we are very lucky at UTS to have a very good machine, an FTIR chemical imaging. Here you've got a little example that was on Gemma's poster. This is a discrimination of two propellants that visually here appear very similar. But when you extract the spectrum at 450 nanometers, here you've got clear differences in the two spectra. Fibers, I'm sure if you ask Dave if he's around, I used to have very good little movies showing how different fibers can behave differently, which is really, really visible for a jury. But here you've got a little two photos showing two different red fibers at 550 nanometers showing fluorescence differences. So this one is very fluorescent, this one not. Gemma did a bit of work comparing that to traditional microspectral photometers. She showed that the chemical imaging microscope system was good to discriminate more fibers in fluorescence mode, especially. This is a little example showing pen inks. I know it's not trace evidence, but many chemists in the room probably might do this sort of analysis. So you can, if you look around here, you can see these three inks there. They are very similar, or at least these two. And if you move in other photos, you can see very clear differences. And the advantage here is because we've got massive amount of data, it's possible to apply a lot of chemometrics. And by looking at different PCAs, it's then possible really to show clear differences. This is the system that we have at UTS. It's an excellent system. Ed was visited us a couple of years ago and had the chance to see this system. So Catherine Flynn is doing this PhD project on trace evidence material for looking at various applications of this FTIR chemical imaging. And this is an example coming from a paper that she recently published looking at typical multi-layer paint chips. And you can see here with a visual image, it may be difficult to see the different layers, but then the false colors here are pretty clear, and it's very easy to see the difference and to see the different layers. Now, because the image is based on the different chemical properties of the material, then it's possible to get a spectrum for each of these layers again very easily. So this is the similar example showing a paint chip with an FTIR chemical imaging. Fibers, we saw this morning very interesting photos of bicomponent fibers. And here, this is an example, again, from one of Catherine's papers. The visible image, it's not that obvious to see that it's a bicomponent fiber. I would even say it's pretty difficult. But by looking at the infrared image, if it's red, it means here, in that case, it's a high intensity. By looking at the amide 1 peak, immediately, so it's very high intensity, so we can get the spectrum. It's nylon, and this is polyurethane. So we have the two different types of polymers for the bicomponent fiber. Another thing that was on Mark's poster, and it's a very interesting honors project that was undertaken last year by Sarah Walker, is to try to use or to detect contaminants within fingerprints. And here the idea is really to detect controlled substances, such as drugs, explosives, gunshot residues, etc. So here you've got an example. So this is the image of the fingerprint. And this is the image taken from the spectra of PETN. And this is the overlay. And when you look at here, all the little green dots within the fingerprints are where the PETN is. So I think this is really compelling evidence showing that, you know, there are traces of PETN within the fingerprint. Sarah and Mark did a bit of study for detection limits, and they show that it was a, you know, pretty good, really excellent detection limits. This is based on paracetamol particles. Another thing that Catherine did, again, it's not really trace evidence, but I found it can be very interesting. It's this old problem of intersecting lines in question documents. And it can be misleading because of the different intensities between toner and ink. And here, by looking at peaks which are present within the toner or within the ink, then it's possible to take a toner image or an ink image and look at the differences. And when you look here at the ink image, you see that this line is broken there. So it's a very clear demonstration that the ink was under the toner. So the C is toner, and this line here is the ink. Now, another kind of technology advances that we've been working on, it's IRMS. I think this morning Bob Blackledge mentioned that for the analysis of rocks. This is a PhD project that we have with Sarah Benson at the Australian Federal Police. It's based primarily on explosives. The idea is to try to use IRMS to identify different sources of explosives. And it's an ongoing project. I can show you a little preliminary result that was based, this one, on PTN, where there were clear differences based on carbon and nitrogen isotope ratios. More substantive results were recently presented at an explosive conference in Paris, but it's a really ambitious project which will bring very interesting results. The objectives here are to develop and validate the method, to determine whether bulk stable isotope analysis could be utilized to differentiate between ammonium nitrates from one manufacturer manufactured over time or different manufacturers. Then the problem to see if we can still use this method post-blast, develop a database which is relevant to the Australian context, or which is mainly Southeast Asian region, and a future focus on peroxide explosives and organic high explosives, but this is another level of difficulties. The third type of technology I want to show here, and it fits very well with what Stephen mentioned before, it's lab-on-a-chip technology. Now, again, we've started this project because there was a lot of money available because of counterterrorism. And we had funding from the equivalent of the TSWG in Australia, which is NSST, for National Security Science and Technology Unit. And Philip Doble, he really champions this project and this technology. The big advantage here is it's a typical type of technology we can bring to the scene or close to the scene. So if there is something like a Bali bombing happening, the AFP would be able to take a box a bit big like that and set up the lab in a hotel room or even closer to the scene. The technology is based on a C, so it's why I said it fits very well with Stephen's presentation. But the big difference compared to what Stephen mentioned, the separation is done on a chip which is probably like that, like half of a credit card. We didn't reinvent the wheel, so we've been using an existing system commercialized by Agilent, but the original application was for life science applications. So when Philip talked to Agilent, talking to them doing explosive analysis, they pretty much laughed at him, but it went really from strength to strength. Here are a couple of examples. This is a detection done in 80 seconds, and you have a good separation of various organic explosives in 80 seconds with the conditions of the electrolyte here. Now, by playing with these conditions, recently it was possible to have a separation in 17 seconds. So this is very, very promising. This is a little experiment, sparking soil with some explosives. And this is the blank soil extract, which is amazingly clean. And here the separation, which was pretty good considering the sample. Now the next step of this project is to combine various components that are available commercially to make a pretty much handheld device for the detection of explosives. And Philip went on the internet, do a shopping spree, buying various systems, buying a mechano set and putting everything together. It's a bit more complex than that, but it's very, very promising. So in discussion, before a quick conclusion, time is running out. I think economic realities and the change of status of trace evidence are really a big challenge for our discipline. So we really need to reassess the place of trace evidence in the whole forensic work we are doing, and especially in relation to investigations. I think trace evidence will re-emerge much stronger within a pretty much short period of time. But how quickly, it will depend on how we work with respect to come back to a more generalist approach, keep a very good holistic view of forensic science. I think it will optimize the value we can get from forensic samples, especially from intelligence viewpoint. It's important to keep a broader view on the various types of evidence. 2, the successful implementation of relevant emerging technologies. There is a lot of technologies coming up. I think we really need to look at them, but in the same time, be careful, avoid to fall in the gadget trap. Really have a clear view about what we want to do and use the technology as a tool. I think the successful implementation of the relevant emerging technologies will blur the boundaries between lab and field forensic sciences. When we see this sort of lab on a chip, it's pretty clear that what's laboratory, what's field forensic science. Because of that, it will streamline the analytical process. I'm not advocating here that we shut down the labs. It's not that at all. It's pretty much to have better systems, to have a quick, better triage closer to the laboratory. And then only the relevant, time-consuming samples are taken back to the laboratory. And in doing that, hopefully, and probably some managers will disagree, they'll say, oh, I can get rid of a few scientists. My point would be, doing that, we free up time for forensic scientists who can then spend more time to do all these little surveys, like Patrick's study this morning, to get all this data. So we can't complain saying, oh, we have too much backlog, we cannot do this, I don't know what it means, because hopefully there will be more time. The other thing, I'll come back to that, I mentioned that on Tuesday, again, to really remember, discrimination is not the only thing. The extreme discrimination is not the only thing. We can have very simple class-level discrimination sometimes, and it gives the information we need. Look at Ken's little experiment during lunchtime. It's pretty interesting. I think we should engage a bit more with DNA and the fingerprint disciplines. Basically, both of them are trace evidence. Maybe you would disagree, but it's trace evidence in nature. It's some transfer, persistence, and detection, collection, and examination of some small amount of material. And many issues are probably the same, and maybe we can find common solutions. So if we have a more coherent approach, forensic science overall will be the winner. So for all these reasons, I think the future of trace evidence is probably much brighter than one might think. I think we should just face the challenges, seize the opportunities where they are, convince the stakeholders. I know it's probably easier for me to say that now like that, but it's something we should try to do. And if we implement the right strategic directions, we support research in the areas where there is a need for research, we will not only save trace evidence, but will really prompt its re-emergence. So a few acknowledgements of various organizations here that have supported us for these projects. I should also acknowledge all the co-authors I had on my first slide. Hopefully I haven't forgotten any. But as you can imagine, this is really a big teamwork. And if I was lucky to go on a 20-hour flight to be the front man here, I'm not the only one to work here. And I think the reality is far the opposite. So otherwise, thank you for listening, and see if there's any questions.